Optimization problems involving rational function models. So the derivatives might not be quite so simple. The equation solving might not be quite so simple. We might have to watch out for continuity issues, and we may need to use the quotient rule. There's also some unit problems that appear in here, so a little piece at a time. Aaron and Tony are creating rectangular banners for the companies attending a convention. Each banner must have a colored border and a white center. This is true about just about all printed materials. If you look at the sheet that you printed out there, I don't know if you noticed, there's like a white border around the outside. They call it the margin when they print out stuff. Makes it look better, that it doesn't print right to the edge. But if you look at any poster, take a look at the posters at the back of my room. All these posters, whether they're colored or not, have like a fancy border around the outside. Somewhere along the way, someone decided to leave a little space around the outside because it looked good. Yeah? And you'll see that in just about any poster or printed material you'll see. That's what this is talking about. Each banner must have a colored border and a white center. So actually, this poster here, my slope poster, is the perfect poster to talk about what they're referring to. Is each of these posters is going to have this border around the outside where there's no printing, and then the center is where the main part of the poster is. The width of the border will be 20 centimeters at the top and bottom and 15 centimeters along the sides. Oh, well, let me draw a picture there. What did they say? Colored border and white center. Okay. Let's see if I can pull this picture off here. What color am I going to make these borders? Red, I guess. So I want a red filled rectangle. That's what I'm after. Am I going to get a red? Oh, there it is. And then, same thing except a white filled rectangle. Yeah, something like that. Good. The width of the border will be 20 centimeters at the top and bottom. So this is 20. I can read my white writing here. 20 centimeters top to bottom. And that's true at the top and the bottom? Yes, 20 centimeters at the bottom too. And then 15 centimeters along the side. So these borders on the side, they're only going to go with 15 centimeters along each side. Like that. Because the number of companies and the available wall space, each banner must have an area of 2.43 meters squared. What are the dimensions of the banner if the area of the white center is to be maximized? When I was teaching these word problems there 10 days ago, 2 weeks ago, whenever it was, what I said was, don't read all the details the first time. Don't let your brain get confused about all the details the first time. Just scan through it until you find the most important sentence. And so I'm going to get out my yellow highlighter here, and I'm going to scan through. I'm going to read this again the way you should read word problems in calculus. Aaron and Tony, creating, okay, each banner must have a colored, okay, width 20, whatever. Yeah, what did it? Oh, area of the white center is maximized. Yeah? That's the important sentence. And hopefully as I do this next part, you're like, oh yeah, this is coming back to me now. Here's my plan. I'm going to find an equation for the area of the white center. Then I'm going to take its derivative. I don't know when. You don't need to copy all this down. This is just my skeleton because it might not fit. I might have to erase it by the time it's all done. I don't know how much space I'm going to need here. At some point, I'm going to take the derivative of the area of the white center, and then I'm going to set that to 0. And then down here, I'll just write check, because we learned 2 different checks by the end of that last week there. We learned 2 different ways to check if it's a maximum or a minimum. Those are the steps of doing these word problems. The skeleton plan's all right there. I mean, if you got to a word problem you really didn't know what to do, at least write that down to get yourself figured out what you're going to do. Now, I'm going to still call that step 1. But moving forward, there should be a step 0 in any problem with measurement involved. So there now should be a step 0. And here's the step 0. I'm going to try and read it. And instead of my yellow highlighter, I'm going to get out my red highlighter. Because when it happens, I want you to have like a sixth sense about this from now on, because I gave it this sixth sense to you. Here I go. Aaron and Tony are creating, each banner must have a colored border and a white center. The width of the border will be 20 centimeters, the top and bottom, and 15 centimeters along the sides. Because of the number of companies, the available wall space, each banner must have an area of 2.43 meters squared. There's a big problem, like a major structural problem in this question. Everything's going to go wrong unless we deal with that at some point. Look at, do you see it? Oh, red. Red, I said. Oh, that's too dark. How about, we'll go with pink. Meters. Still don't even like pink. I want you to be able to see it plain as day. Orange. Meters. And up here, centimeters. At some point, I have to deal with that situation. Now, everyone's different as far as which way they like to switch. I like switching. I'm fine with decimals. But some people don't like that. They want to go to numbers and get big numbers here. Because when I switch over, one of them's going to get bigger or one of them's going to get smaller. And I got to decide whether I'm going to work on this question in centimeters or whether I'm going to work on this question in meters. Got a choice to make. And it's worse than you think. You may have never seen this before. This squared thing is a big problem. I'm going to a new flip chart to talk about this, to talk about converting centimeters squared to meters squared. New rectangle. I'm just specifically talking about converting things over. Let's talk about this rectangle for a second, and let's just pretend for a minute it's 1 meter by 2 meters. Something pretty simple. Would make you want to work in meters. 1 by 2, how nice is that? But if I had to work in centimeters, I'll do the area here. Area equals 1 times 2 equals 2 meters squared. If I had to do it in centimeters, watch what happens. This becomes 100 centimeters. This becomes 200 centimeters. And the area is 100 by 200, which is 20,000 centimeters squared. It's not what most people would have said. They would have said, oh, meters squared to centimeters. When you go from meters to centimeters, you multiply by 100. And that's absolutely true. When you change from meters to centimeters, you multiply by 100. But when you go from meter squared to centimeter squared, you've got to multiply by 100 2 times. Once for the length and once for the width. It's also true for cubed. When you go meters cubed to centimeters cubed, you got to multiply by 100 by 100 by 100. You got to do 1 for each dimension. Okay, so watch out for that. We sort of hid you from that all the way up through the grades right now. We just went, okay, always meters, centimeters. But the squared ones switch over. And here's a little picture of why it happens, because you might look at it and go, that's insane. Why does that happen? Well, think about this for a second. If I was to do centimeters along here, like little, those little centimeter cubes, those little that you played with when you were a kid, you snapped them together maybe in previous grades. Just imagine me snapping some of those together. I'd have to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 100 of them down here to get 1 meter. Then I'd have to go 200 of them along here. You know, you'd have so many of these little squares that you had to do, and that's why you have to do it both ways, because it's not just, there's an extra 100 right there. Then another extra 100, extra 100, extra 100, extra 100, extra. There's so many extra hundreds. How many extra hundreds? 100 extra hundreds. That's why you have to convert twice. Okay. All that to get back to this situation here, this 2.43 meters squared. I, personally, I'm not scared of the decimals, but me personally, I'll always stay away from the decimals if I can. And so I can stay away from the decimals before I even start this question by going, this is 24300 centimeters squared. Some people like working with smaller numbers. They'd much rather work with a 2.43 and 0.15 and 0.2. You can do that too. Either way. But if you're going to convert to squared, you've got to be ready. You've got to multiply by 100 twice. So I multiplied by 100 and got 243. Multiplied by 100 again, I got 24,300 centimeters squared. But your choice. I could just as easily do this question with 0.20 and 0.15, and that works out fine as well. Either way. Okay. Now I've got another big decision to make. So that was like step 0. Step 0 is like, okay, get the units all together before I even start. Don't wait around for that. Get it done right off the hop. Then I'm going after area of the white part. So I got a decision to make. I've got an L and W I want to put on here, and I've got a decision to make about where I put L and W. If I put L all the way along here, that will work, but then my area of the white part here will be L minus something and W minus something. So it makes this equation a little more complicated if I choose to put the L and W there. That's fine. Or I could choose to put the giant eraser here. Or I could choose to put the L and W here. And if I do that, my area of the white will be just nice LW. Won't that be a nice, easy formula? But my big rectangle will be more complicated. And the only reason I told you about both is it's just a trade-off. Sometimes it'll be way better one or the other, and you'll know it as you go to do the question. But most times it's just a trade-off about when it's going to be complicated. Because in a situation like this, some along the way it's going to be complicated. You get to choose when. Me personally, I like to keep my one that I'm going to take the derivative as simple as possible. That's what I find. But I'm wrong sometimes. There are questions where you'll come up to me and you'll say, oh, I kept it as simple as I could, just like you said, and I can't get it done. I'm like, yeah, I know. That one you have to do it the other way. Yeah? So just be ready to change where you put the variables, only to make your life easier. You can do it either way. You'll always be able to do it either way. It's just about how complicated you're going to make certain steps. You'll see what I mean by the time I get to the end of the problem. Look, area of the white, L times W. I put L there and W there to keep my derivative equation very, very simple. Something else is going to happen in a minute, and I'll get to that later. See, I've left this unlabeled, like, oh, I don't even have to worry about it. Oh, it comes up. Watch. LW. What's the problem with this equation? Rewinding back 10 days, I'd like to take the derivative of this nice LW equation, but there's a major league problem with taking derivatives in situations like this. What's the major league problem? Simon. There's two different variables. And I've dramatized that moment on purpose because I want you to be very motivated to go, with two variables, there's another step in these questions. If it was just take the derivative, I wouldn't need three separate lessons to teach this. You just take the derivative, and if even it's complicated. You did so many complicated derivatives in Unit 4, you wouldn't even care. Look at how easy this derivative really is. It's just two single variables, no squares, no square roots, no cube roots. It's beautiful, except for the fact that it's two variables. So then there's got to be some other piece of information that allows me to do some modification to this equation so that it doesn't have both L's and W's in it. So I go back to the picture and I go, well, what relationship is there? It's this. It's actually called a constraint. And I'm going to give it a name to try and help you label it. You don't need the name in this chapter. You don't need the name on this test. It'll come up in later courses. But it's called a constraint, and it says, well, yes, find the derivative of this, but under this constraint, this has to be true about the situation. The area of the whole banner has to be 2.43, and this is the difficult part of the situation. Because they said the area of each banner, the whole banner, not the here, the area of the whole banner has to be 2.43. What that means is this length times this width, the whole, all the way across the banner. And now the complicated part comes back in, which I seemingly avoided, but now I find out I haven't avoided it at all. I've just got to deal with it here. See, this length here is L plus 40. I'm working in centimeters. And this width here is W plus 30. And so my constraint, and now I'm going to erase this whole skeleton here. I haven't forgotten about this skeleton I wrote out here, and we'll get back to all these steps that I wrote here. But L plus 40, I said 40 and then wrote W because I was already getting ahead of myself, times W plus 30 has to equal 24,300. That's the constraint that I have to deal with in this situation. Now, just rewind to make sure what my goal was. My goal is to try and get L or W by itself. I don't really see that one of these L or W's is going to be easier to solve for necessarily than the other one. If there is a situation where it's like, oh, it's easier to solve for this or it's easier to solve for this, then you definitely want to take advantage of that. But here I don't really see any way around it. So here I go to try and solve for L I've decided to do. And if you're really with me, you might see why this equation, or this question is going to be a little more complicated derivative-wise, a little more complicated. After Unit 4 is that we've taken care of Unit 4, it won't be unmanageable at all. I got